Okay, the next concept we're going to be going over back to kind of the periodic table again. We talked a lot about phases, solid, liquid, and gas. And so you can actually see that, remember when we talked about phases on the periodic table, we said that's at room temperature. Well, not everything's always at room temperature, and not everything is actually at a normal standard atmospheric pressure either. And you should know from experience that, for example, if you have a bucket of ice and the temperature goes up, it melts and turns to liquid, right? So that's a phase change. It's going from solid to liquid. And the way that happened is temperature. Everyone knows about temperature, right? And then I boil the water that I have, and I raise it to 100 degrees Celsius. It starts boiling, and the temperature is going up, and then it vaporizes, or for water, it kind of boils as well, vaporizes into a gas water vapor, right? And then same thing can happen in reverse as well. If it gets cold enough, the water vapor can condense. You've probably seen that maybe on glass before in the early morning. It can condense here into liquid. And then if you put water in the freezer below its freezing point at standard atmospheric pressure, it will just turn into ice. So it will freeze again. And so we know about these phase changes now. But there's also another phase change that's not very commonly talked about. It's solid to gas and gas to solid. If you guys have seen dry ice before, they're like these solid chunks, and you can see carbon dioxide gas just like floating off of them. So that's solid turning into gas. That's called sublimation. And also you can have the reverse reaction, which is gas turning into solid again, and that's called deposition. So we talked a lot about temperature and how that causes a lot of changes, but you can actually also force changes out of pressure. If I take a bunch of gas, like let's say I'm over here, and I take a bunch of gas and I put it under a very high pressure, I can force it to liquefy. And at very low temperatures, I can actually force gas to liquefy directly into solid as well, as you can see from this diagram. And then so there's both a temperature and a pressure component to changing between phases. Now let's talk about the other two things we haven't talked about on this graph, which are these two dots. One of them is the triple point. So notice that there's like a sector of the graph that's for solids, there's a sector of the graph that's for liquids, and there's a sector of the graph that's for gases. And these all kind of intersect here at this one pressure and temperature called the triple point. And so at the triple point, which for water is like, I think 0.1 degrees Celsius, all of these kind of phases are in equilibrium. And if you change the pressure, the temperature just a tiny bit, you can switch between all three phases of matter. So you can go, I increase the temperature a tiny bit, it turns into a gas. I increase the temperature and pressure a tiny bit, it turns into a liquid. I decrease the temperature a bit and it turns into a solid. So you can, that's the triple point where all these phases and their temperatures and pressures kind of meet together. The other point you want to know is the critical point. And I want to bring your attention to this graph on the right to better understand the critical point, because I think it's a better drawn graph. So as you can see over here, what we have is that I said that if you pressurize the gas, you put it under enough pressure, it'll turn into a liquid. But this is only true up to a certain point. At a certain point, no matter how much you pressurize the gas at a high enough temperature, no matter how much you pressurize the gas, it will no longer turn into a liquid. And so we call that point where the liquid and the gas phases, they kind of get muddled together, the critical point. So beyond the critical point in temperature, the critical temperature, you can no longer use pressure to liquefy a gas. And instead, what you'll get is the supercritical fluid. And so the supercritical fluid here, as you can see, occupies just this region of the graph after the critical temperature and the critical pressure, which is just the pressure at the critical point. The supercritical fluid has the properties of both gases and liquids. It's like kind of in between. So for example, it can effuse through materials. So kind of like gas escaping out of like boxes, because like you prick holes in a balloon and the gas kind of flies away, or it just kind of goes through the pores of the material. So supercritical fluids can do that, for example. And so supercritical fluids have both the properties of the liquids and gases in part. Okay, quick other things, chemical reactions, which we touched upon before. Just know that there are 4 basic types of chemical reactions. I'll try to give examples here. The first one is the synthesis reaction. You have 2 more basic kind of reactants, and they turn into something that's larger, more complex. So you have, for example, let's say you have sodium and chlorine, and you put them together, you get sodium chloride. So Na plus Cl gives you NaCl. So that's a synthesis reaction. Decomposition is just the reverse. I have NaCl, it turns into Na plus Cl. You have the single replacement, which is that, look, you have like NaCl and you have F, for example, fluorine, and then they just switch places. One of them switches places with the other. So that's a single replacement. And in a double replacement, you have like both of these partners are swapping with each other. So one of the partners is swapping, both of the partners are swapping here in the double replacement. So just know that these 4 basic terms And one of the last things we're going to cover today is acids, bases, and pH. So now that we've gone through all this stuff about the periodic table, we're going to talk about another concept which you might have commonly heard about in life, but you might want to know more about chemically. And those are acids, bases, and pH. So pH, the power of hydrogen, is a way of measuring acidity and basicity. So you might have heard something that's very acidic, right? I eat lemon, ever since that's very acidic. And so the pH scale is from 0 to 14. Those are just numbers. The pH of water is defined exactly at the middle, 7. There are 3 kind of systems that people could talk about in terms of acids and bases: Arrhenius, Bronsted, Lowry, and Lewis. And we're kind of running a bit short on time here. So these are just names you can write down. You can look them up if you want to know more about acids, bases, and bases. But just know that this concept of pH, different people have been trying to define it in different ways throughout the centuries. And these 3 are all people, or actually Bronsted, Lowry's, these are all ideas made by people, scientists, about what pH means, what acidity means, what basicity means. And so the general concept you'll need to know is that an acid tends to release, kind of like in terms of the Arrhenius definition, the most basic definition here, an acid kind of tends to release these hydrogen ions and into water. So when this H plus combines with H2O, sometimes it makes this H3O plus called hydronium ion. But it tends to release these hydrogen ions and make these hydronium ions in water. And then Bronsted, Lowry said essentially that bases, they tend to release this OH minus called a hydroxide ion in water. So just to summarize there, Arrhenius says that acids release in water, they release this hydrogen ion that forms these hydronium ions in water. He actually says bases are just substances that accept these hydrogen ions. So acids release them, bases accept them. Bronsted, Lowry said acids release this H plus ion, and the bases release this OH minus ion. And Lewis had a completely different idea, kind of very similar, but he defined it in a lot of different ways. He talked about electrons. And so we're not going to cover that today, but just know that in general, when you see these ions, associate H plus and H3O plus with the acid and OH minus with the base. And so here's a nice scale that shows you everything. You have like battery acid, right? We talked about tomatoes are acidic, lemons are acidic, water is neutral, Tide Pods, drain cleaner, bleach, those kind of, sometimes those harsh cleaning substances you tend to think of, ammonia, those tend to be basic. And it's not that basic things are worse than acids. For example, acids will burn your skin off, but bases will kind of just cause it to painlessly peel off in layers off of your body. So these are both very dangerous to you. And it's not that one is worse than the other.